Hi everyone, in this video I'm going to compare and contrast what we call paired samples versus independent samples. Last time you will remember that we compared the change in L parameter, that is how skin luminosity changed from baseline to D28, and we discussed that the samples could be considered as paired for the simple reason that the observations on one particular row correspond to the same individual and they share so many things in common. Today we are going to look at a case of independent samples, and we are going to avoid to take a chromometer again. We'll shift to another instrument, so at the same time we are looking at different instruments. We take an example of a randomized clinical trial to compare efficacy of two formulations, let us say A and B, against skin aging. So it stops here. So when we think of skin aging parameters, we tend to think of elasticity, etc. And immediately the instrument that comes to our mind could be a cutometer. I don't want to go into the physics behind what the cutometer does, how it works, etc. I don't do that, I'm not the expert in it. But even if you don't know, there are some tricks here and there that you can use to understand the basics and how you can make clinical interpretation out of the values that you obtain during the measurements. Now, as usual, I like to write the study objectives clearly. So to compare the efficacy of two formulations A and B. Now, very often what I notice is that in protocols, authors, they don't write this part. Now, this is not correct. When you say efficacy, you have to mention efficacy to do what? Is it to enhance skin color? Is it efficacy to protect against sunburn? What is the product doing? You need to mention this part. But this part, that is, how do you assess the efficacy? This is normally described in the methodology. We write it here just for the sake of convenience, that is, it's easy for the reader once looking at it, okay, you know what's going on. But normally you will describe all these, that is, you are going to use cutometer, clinical evaluations, etc., etc. Normally it's described in the method. You write it here just for the sake of convenience. Because I don't know anything about cutometer and skin aging, the thing that I'm going to do is I'm just going to make a quick search, cutometer and skin aging, and I see what it gives me. So hey, I get so many articles here, and I'm going to choose the very first one, and I see what it says. And interestingly, if you read the article, you will see that it tells you, hey, you know what? Age was positively correlated with R4 and R6. That's interesting. And then negatively correlated with R2 and R5. So that gives us somewhere to start. And you can try to get the full article as well. That's not very complicated nowadays. Even if you don't have a subscription, you can try it. You can ask the authors, you can write to them, or things like that. So if we come here, we see, okay, it's properly described, and I see again that I see the methods. Well, that was already in the abstract, and I see again age positively correlated with R4 and R6. I have a look at the method. I see whether the study is a reliable one. Does it look like there is some good work that has been done in the background? I check a bit the referencing, etc. So I say, okay, this is one of the things that I can consider. I don't have to stick only to one. I can check other articles as well, but I'm doing this very fast. Many of you will recall that when we look at cutometer measurements, so we've got a set of parameters in the form of R0, R1, R2, etc., up to R9. And then we've got another set of parameters, UA, UE, UF, UA minus UF, UA divided by UF, etc. They are basically the same thing, and this is what is described in this part of the article here. You will see it describes clearly what this means. So you will see here, for example, what is UA, what is UA starting from here, UA up to here. I think you will see all the parameters are properly described. So it's basically the same thing. You can look at the equivalence. So in the article, we found that age was positively correlated with R4 and R6. So I can say that when age increases, these two parameters, they are going to increase as well. So you can imagine a sort of a graph here where we've got age on the x-axis and here we've got R4. We are saying that, let us say age is here, someone's age is here, R4 would be somewhere here. If we increase age, there is a positive correlation, meaning R4 is going to increase as well. So we can imagine a sort of a scatter plot somewhere like that. Okay? It's the same thing for R6, but on the other way around, in the article, it says that when age increases, R2 or 5 or 7, they are going to decrease. Okay? This is a scatter plot. Now, it's not a deterministic relationship. It's a stochastic one. It's statistical, meaning that you may have someone here who is very old, but R6 is relatively low. On the other hand, you may have someone who is very young, but R6 is relatively high. What we are saying is that on average, when age increases, R6 increases as well, and the other way around for the other parameters. So basically, we've got these parameters. This is very interesting for us, and this is what we are going to do to be able to conduct our study and statistical analysis later on. Now, if we stick to these three parameters, just for an example, I'm going to concentrate on R5, for example. So we have seen that when age increases, these parameters, they tend to decrease, okay? And I ask you, what is considered as a favorable outcome? Do you prefer lower R5 or do you prefer higher ones? So if when age increases, these parameters, they decrease. So in other words, one wouldn't want those to decrease. So in other words, we are going to write that the higher the R5, the better it is. This is what we prefer. We prefer bigger and bigger values of R5 because when it decreases, it means that in fact it is a sign of aging. When age is increasing, these parameters are decreasing. So we are going to say that we prefer higher values of R5, and it applies to R2 and to R7 as well. We are focusing on R5. And also, it is worth noting that R5 is the same thing as UR divided by UE. Okay, it's the same thing. The equivalent in terms of the original parameters, it's UR divided by UE. So now you conduct the clinical trial. The first subject is assigned a product according to a randomization schedule. The randomization schedule is normally generated by a statistician. So according to the randomization plan, it can be also in an online setting, but we are not going to go into these details. The first subject needs to get product A, and when you take the cutometer readings, on D0 it was 0.7, and on D28 it turned out to be 1.35. Don't forget that we are looking at the parameter R5, which is characterized, which is also given by UR divided by UE. And what we have said We have seen that when age increases, we have seen that R5 decreases. So which means that we are happy with higher values of R5, okay? Because if it goes down, it is indicative of aging. So for example, for this first subject, we are quite happy about it because it went from 0.7 to 1.35. For the second subject who used product B, there is an increase as well. For this one, and it goes on like that. So there are on occasions you will see bigger increases, on some occasions you will see smaller increases or even a reduction. So this is normally how the data set should be. As you will see, what I could do something like that. I could have a data set, I would say, this is for A, 7 to 1.35. The next subject that comes here is going to be subject 3. And it goes on like that. Here it's going to be subject 2, and here it's going to be subject 4. I could do that as well, there is no problem as such, but bear in mind that the real structure of the data is this one below the other. Why is it so? Because you know, look at this row. When you look at this row, we are writing 1 next to randomization number 2. These two subjects, they have nothing in common. I could just swap randomization 2, I could put it here, 2 and 4. It doesn't make any difference. Likewise, I can say, I can put randomization 3 here and I put 1 here, but of course I have to write the corresponding values for 3 and 1. It doesn't make any difference. We can write it next to each other, but you have to bear in mind that they are not paired. These two samples are independent. The real structure of the data is one below the other. I could write all A's and all B's below. Doesn't make any difference. That's still good. For the sake of convenience, if you do it that way, fine, fair enough, but bear in mind that these two are not paired. You can end up having for A values stopping here, but for B it goes up to here. The sample sizes for the two groups do not need to be exactly the same. So, and here we are looking at a randomized clinical trial, and in this case we are assuming that two groups of subjects have tested two products separately. It could be also in on the same subject. For example, you are testing product A on the forearm here, B on the other forearm. Same subject who tests both products. Then it's going to be a paired design. But when you've got two groups of subjects testing two products separately, then the design is independent, two independent groups, and you have to cater for this even in your presentation as far as possible. Now that we have seen that for product A, R5 increased, while for product B, it remained fairly stable, we want to see whether the change was significantly different between the two groups. In other words, we want to compare this difference data versus this difference data. So to be able to do that, now we are looking for the p-value. It equals to t-test. You select all these, comma, all these, comma. 2 means a two-tailed test, meaning that one could be better than this one, or this one could be better than this one, comma, 2. Remember, the second 2, it means whether we are looking for a paired or independent samples. In earlier videos, we have used 1 because we were looking at paired samples. Right now, we are looking at 2 independent samples. So it equals to 0.03, which is less than the conventional or traditional 0.05 level, that is 5% significance level. So we can write the conclusion that R5 this indicates the capacity of product A of maintaining skin aging parameters levels after 28 days of production. So you can write something like that. So R5 was found to increase for those who use product A. Yeah, it remained comma here, it remained fairly stable for product B. Difference was significant. Yeah, statistically significant between two groups. B value. Product A maintaining skin age values at low levels. Here you go. That's it. Now, when you have finished writing this conclusion, you need to pray. You know what you need to pray for? You need to pray that product A was the right product that the sponsor wanted to test, and that product B was most probably a placebo. Now, if it was the other way around, and that product B was the one wanted to be put forward by the client, so you need to get ready. The client is going to come after you and will try to tell you that the product, that the study was wrongly done, the evaluations were wrongly made, that you have swapped the product, etc., etc. So you need to make sure that you have performed the study well and that you have respected the protocol, and make sure you haven't swapped the product, because in a study like that, you don't know what is A and what is B. You may be lucky if you have some clue, but generally in a randomized and double-blinded study where the investigator and the subject both are unaware of the product being administered, so you have to be very careful. Well, you have to always be very careful, but here you just pray that you are a bit lucky as well. Thank you very much. I hope you enjoyed the video.